Let's get shocked, shall we? Electricity. Now, Unit 4 is split into two parts, so electricity and magnetism. Today we're just focusing on electricity. And overall, this unit is about charges. So what's a charge? We discussed the charge within the structure of an atom, how like protons and neutrons and protons and electrons have positive and negative charge. We'll deal with that again. So we split this unit into static electricity portions. So what's a charge and what's an electric field? It's a very minor topic. Then we talk about electric circuits. We'll start by talking about the properties of a circuit. So what quantities do we measure? Voltage and current and resistance and power and such. And then we go into series and parallel connections and multiple components and so on. Once we're done with that, we'll just finish things up by talking about electrical safety because, electricity can kill you and we do want to keep you safe. At least you should know how to keep yourself safe. Let's start. Before we continue, the same friendly reminder, this checklist, this list of topics, is from the curriculum. I want you to use this as a checklist to see if you understand the topic or not. So, for example, if you say that state that there are positive and negative charges and you understand that, I'm sure you do, you're fine. If not, you need to revise that topic again. Okay. Let's start with static electricity. First, when we talk about electricity, we have to talk about the electric charge. A charge is a property of matter that experiences forces near other charges. What do I mean? This means that all matter in the universe has charge. Whether it's a proton, neutron, electron, matter, me, you, everything is charged. But there are two different types of charges. There are positive charges and there are negative charges. And they're opposites. Things can either be positive or negative or neutral. Neutral objects are neutral because they have both positive and negative charges together. So they have a resultant of zero charge. Charge is measured in a unit called coulomb. Now, I want to focus on this for a second. The charge of one proton is 1.610 to the power of negative 19 coulombs. And the charge of one electron is negative 1.610 to the power of negative 19 coulombs. You don't have to memorize these. Please don't, okay? But what I mean is each proton or electron, like subatomic particle, isn't one charge, isn't one coulomb of charge. It's actually like a fraction of a charge. Because later on, when I mention something like, hey, the charge is going to split, it doesn't mean that we physically break a charge. If you have one coulomb, you actually have millions of tiny little particles stuck together. And yeah, sure, these can split and travel. 0.1.0 can travel here, zero point 0.6 can travel here. It depends. So later on, when we say half an ampere, 2 amperes, current splits, this is why it can split, okay? Now, the relationship between charges is very basic, and I'm sure you know. Like charges repel, so positive and positive repel, negative and negative repel, opposites attract, positive and negative attract. However, neutral objects can also be attracted to charged objects, whether it's positive or negative. Why? Because inside the neutral object, we said you have both positive and negative charge. And these rearrange so that the positive is closer, so attraction is a bit stronger. And the same thing happens here. If you have a negatively charged particle next to something neutral, the positive and negative rearrange so that the positive is closer and the attraction is stronger than the repulsion. Regardless, anything neutral is attracted to anything charged. Yeah. When it comes to materials, we have two types of materials: good conductors of electricity and bad conductors of electricity, which we also call insulators. Conductors are good conductors because they have free-moving electrons. We sometimes call them delocalized electrons or free-moving ions. So it's electrons that are free to move. You should know that all metals are free-moving electrons. So copper, iron, aluminum, constantan, nickel, whatever it is. Insulators do not conduct because they do not have free-moving electrons. Somebody forgot the letter T here when typing this sheet, aka me. Oh, well, do not have free-moving electrons. Things like rubber and plastic and glass and wood, you should be familiar with different types of insulators. However, even though insulators cannot conduct electricity, they can be charged. Like you can make them become charged by rubbing them with another insulator. So for example, if you rub a metal rod with a cloth, a wooden cloth, for example, a plastic rod, not a metal rod, a plastic rod with a woolen cloth, the friction between the rubbing of the cloth and the plastic rod causes some electrons to be transferred from one object to another. The cloth could lose electrons and give it to the rod, or vice versa. This depends on the materials, and we're not going to study which materials lose or gain. But you do need to know that if an object loses electrons, it becomes positively charged. If an object gains electrons, it becomes negatively charged. Okay? Good. Right. You cannot do this with conductors, by the way. And this is something that was removed from the syllabus in 2023. How do we charge conductors? And it's a method called induction, but it's not part of our curriculum anymore. Okay? So keep that in mind. Next. What is an electric field? Now, the word field in general means a region, a space where something experiences a force. So an electric field is a region where charges experience a force. Okay? What is the direction of an electric field and how do we draw it? We draw the direction of electric field using straight lines coming out of a positively charged point. So it's always out of a point. Or if it's a sphere, it's always out of the positively charged sphere. Or if the point is negative, it's drawn into it. The question is why? Like, why do we draw the field lines like that? That's because if I zoom in and I tell you, hey, if you decide to put a positively charged particle here, what's going to happen to it? It gets repelled. What about a positively charged particle here? It gets repelled. So each of these lines shows you the direction of the force on a positive charge at that point. Which means if you put that same positively charged particle here next to the negative point charge, it gets attracted. Right? It gets attracted. So you might say, what about electrons or like negative charges? Shouldn't we draw those? Like, we don't have to. We know that positive and negative are always opposite to each other. So if you have a negatively charged particle here, it'll be attracted, or here, it'll be repelled, which means negative charges always move opposite to the direction of the field. Okay? So when I ask you to draw the field lines, you always draw them going out of a positive charge or into a negative charge. Out of a positive or into a negative. Now, one more feature here. The space between the lines shows you how strong a field is. So if you take a look at this field diagram, this is the same field, but now it's a metal sphere that's positively charged. Or maybe it's a plastic sphere, we don't care. But the closer the lines are together, the stronger the field is. And the farther away the lines are from each other, the weaker the field is. Which makes a lot of sense if you think about it, because the field has to be stronger near the charge and weaker far away from the charge. So if I put two charges, one here and one here, and I ask you which one experiences more force, like they both get repelled, but which one experiences more force? B experiences more force because A is further away and the field here is weaker. Finally, if you put a positive charge in front of a negative charge, a plate in front of a plate, you end up with an electric field that is equally spaced, almost at least. This type of field is called a uniform field, and we always draw the field lines from positive to negative. Right? A uniform field means the strength of the field is constant everywhere in that space. Now, let me draw one more diagram, something that sometimes shows up. Not always, but then. Imagine that you have a positively charged sphere and a negatively charged sphere, and I ask you to draw the field line between them. So you draw lines from positive to negative, but because they're spheres, the field still gets weaker as you move further away. So out of the positive, into the negative. So it's as if I tried to join these two fields together. I'm sure you can see it now. But the more interesting diagram is, what if I have a positive charge next to a positive charge? Sure, they should repel, but they don't just physically repel, even the fields repel. So the field lines don't even touch each other. Out of the positive, out of the positive. Do you know what that means? This means that if I zoom in here and I put something perfectly in the middle between them, it doesn't move. If I put a positive charge exactly in the middle, it doesn't move because this space is a null space. There's no field here. Zero field. Okay? Now, let's solve a couple of questions. Figure 8.1 shows a negatively charged metal sphere. Draw 4 lines, just wants 4, to show its electric field and its direction. Let me pull out this line tool. And let's draw. While I draw, I'll answer a question. What if I put a negative charge exactly in the middle, in that space, in that null space? Nothing as well. Nothing moves. You might say, but it gets attracted. Yeah, to which side? You don't know if it's perfectly in the middle. Now, because this is a negatively charged sphere, you draw the lines going into it. Piece of advice. If I draw a sphere, do not draw the field lines going inside the sphere. You should draw nothing in here. But if this was just a negatively charged dot, sometimes called a point charge, and I ask you for the same thing, yeah, you can draw lines exactly through it. And it'll look exactly the same. Okay? So be careful. If it's a sphere, nothing inside the sphere. If it's a point charge, yeah, just go through it. That's fine. A plastic rod is rubbed with a cloth. The rod and cloth become charged as electrons move between them. The rod becomes negative, which diagram shows how the rod becomes negatively charged and shows the final charge on the cloth. All right. Now, if the rod becomes negative, this means it has gained electrons. It has gained electrons, which means the cloth becomes positive. So this gains electrons, and this becomes negative, and this becomes positive. So my choice is B. As electrons move from the cloth to the rod, and this becomes negative, this becomes positive. Easy. All right, I have another question. Do we draw arrows or just... Oh, yeah, absolutely. When it comes to field lines, you must draw arrows. Otherwise, why did we go over explaining drawing the lines? Because the lines show you the direction of the force, and force is a vector. And fields are vectors, by the way, because they have direction. You have to show the direction with arrows. Lines going into a negative or out of a positive if it's a positive charge. Okay? You mean we draw 4 lines, or do you need to do more? I mean, I'm sorry, but you're given instructions. Listen to them. He said 4 lines. The examiner said 4 lines. I draw 4 lines. Come on. All right. Next up, current electricity. Another giant checklist because it's full of tiny, tiny little dots. I'm not going to read the full checklist. I want to go straight into current and voltage and resistance. Before I do, however, before I talk about current or voltage or resistance, let's talk about circuits in general. The purpose of any electric circuit like this one is to deliver electricity. A battery is a source of energy. It has chemical energy inside. Or maybe this is an electric socket, so it's just electrical energy directly. The point is to deliver the electrical energy from the source of the energy that you have to my target that needs that source. In this case, it's what? It's the light bulb. So electric charges travel through the circuit to give that thing energy and it leaves. But in order to do so, there needs to be a force acting on it. For the time being, and I'm going to change my mind very quickly now, I'm going to assume that positive charges are moving inside a circuit. Now, in any circuit symbol, before I move on as well, the long line of the battery symbol is positive, the short line is negative, right? So when I close a switch needs to be closed in order for the circuit to work. The term open means the circuit's not going to work. The term closed means the circuit is now going to work because now it can conduct electricity. Now, the moment, I don't know why I want to choose the entire thing, please. Thank you. There we go. The moment you close the switch, a positive charge gets pushed out of the positive side of the battery, zoom moves through because it gets repelled. Now, because it was pushed out, it now has energy. It goes through the light bulb, which is the target, which takes the energy away because it has resistance. It slows down the charge, and takes the energy away. The charge is still positive, but it leaves without energy and goes back to the negative side of the battery to essentially recharge, again, get some more energy, gets pushed out, and you end up with a sequence. And you end up with a sequence, a current that flows. So when I say, what is a current? And I ask you, what is a current? You say it is the rate of flow of charge or the amount of charge that passes through a point per unit time. Now, charge is measured in Coulomb. Current is measured in ampere, where 1 ampere means 1 Coulomb per second. So there's one charge that goes through the circuit per second. The equation that defines electric current is I equals Q over T, where I is current. Now, the reason we use I for current is because I is current is actually short for electric current intensity. So they got the I from intensity. Q is for charge. I don't know why they chose Q. So many things in physics use the letter Q. And T is for time. So current is just how many charges go through per second. We can measure current using an ammeter. And ammeters must always be placed in series. Okay? Now, there are two types of currents that we have in electricity, what we call DC and AC. DC is short for direct current, okay? Not the comic books. And AC is alternating current. Well, I like DC more than Marvel, though. That's my personal preference. Not the movies, the heroes. So what do I mean by DC and AC? DC is a current that has a fixed direction, which means the source has a positive and negative side that are fixed, and the value of the current or the voltage is fixed. So the current flows from positive to negative, and it has a fixed value. That's called DC. AC, however, comes from a generator or your electric sockets, which initially come from a generator inside a power station. Okay? Good. The thing is, the reason it's called AC or an alternating current is because the positive and negative sides of the terminals are never fixed. This side could be positive and this side could be negative. And in the next zero point 0.2 seconds, so if we have like a 50 hertz AC supply, this could be positive and this could be negative. Which means for 0 0.2 seconds, the current flows this way, zoom. And for the next 0 0.2 seconds, the current flows this way, zap. And then zoom and zam, and back and forth, back and forth, back and forth. Very confusing. If I plot a graph of how the voltage or the current changes over time, it looks like this. Positive, negative. The negative sign simply means that the direction has changed. It's in the opposite direction. It looks like a wave, sine wave. Okay? Now, finally, remember how I said there's a mistake that was made? Back when I described the circuit earlier, I said a positive charge travels from the positive side of the battery to the negative side of the battery. Correct? Yes. That's physically not true because earlier in static electricity, we said conductors are good conductors, metals are good conductors because they have free moving electrons, and electrons are negatively charged. So, this thing of us saying, hey, the current's flowing from positive to negative is hogwash. But it's stuck. Why? A very long time ago, scientists did not know what was free to move inside a metal. Like they knew charges existed, they knew they could be positive or negative, but they didn't even know about protons and electrons yet. So they decided that charges need to flow from positive to negative. Why? Because it's easy. Come on. Like positive, negative, it's nice. High to low. And then decades passed by until finally some other, you know, good scientists discovered, hey guys, what's actually free to move inside a metal is an electron, not a proton, not a positive charge. But all our rules in electricity are fine. They work just fine. So what do we do? What we did was we stuck to the concept of positive to negative. We just called it the conventional current, which is the flow from positive to negative. And if somebody asks, what are the actual particles that flow inside a circuit? We go ahead and we, submit and say, oh yeah, we're sorry. It's actually electrons that travel from negative to positive. But we don't call it a current because we don't want to be confused. We just call it the flow of electrons or electron flow. So in all of our circuits, if I ever discuss a current, it is always from positive to negative. We never use negative to positive unless I specifically ask you about electrons. Okay? That's quantity number one. Let's go to quantity number two. Remember, circuit delivers energy. The flow of those charges is called current. The energy that we deliver is called voltage. Voltage in general simply means the amount of energy or work done per unit charge. So voltage is the work done or energy transferred per unit charge. Now, what do I mean by that? I was just changing the battery for one of my clocks here at home. It's a nice, small, Energizer battery. I remember a long time ago when Energizer had these really crazy ads with the rabbit and stuff. Anyway, and it has a positive and negative sign, and written in very small font, this is like AA 1.5V. What is this? If I tell you that a battery has a voltage of 1.5 volts, this means that each charge that leaves the battery carries with it 1.5 joules. If this is 1 coulomb, it carries with it 1.5 joules. Remember, the charge delivers energy. The charge is not the energy itself. This means that each and every single charge will carry 1.5 joules with it. This is the capacity of the battery. This is how much it can give each charge that goes through. It has nothing to do with the maximum amount of energy inside the battery. Because I can buy another, like I have a very old radio. I like to use it. Right? It gives me like nice old vibes, especially when I don't want to use the internet. But these batteries, the battery that the radio uses, are huge, big, chunky, almost like toss at somebody's head and give them a fracture kind of big, called D batteries or DD. I don't remember, but it's also 1.5 volts. What's the difference? They will both give the same amount of energy per charge. The difference is how much it lasts. So that changes, sure. But voltage doesn't specify that. Voltage just tells you how much energy does each charge take and deliver. So when these charges go to the light bulb, they give the light bulb 1.5 joules each. Okay? Now, there are actually two different terms that we use for voltage. We have EMF, which is short for electromotive force, and PD, which is short for potential difference. They both mean energy per charge, but the difference is EMF is the work done or the energy transferred by a source in moving a unit charge around the whole circuit. It's the energy per charge of a source, because batteries give the charge energy. Potential difference is the work done per unit charge or the energy per charge lost through a component, because the light bulb takes the energy away from the charge. So that's why we need two different names for the same quantity, because it's either energy gained by the charge, so we give the charge the energy, or we take the energy away from the charge. But they both have the same symbol as far as we're concerned. It's just V from now on, okay? Sometimes we use E for EMF, but regardless, V is fine. The unit of measurement is called volt, so just V as well. And we measure it using a voltmeter. A voltmeter is this device over here, and it must always be connected in parallel, meaning the wires have to be placed before and after the thing that you're trying to measure the voltage across. Okay. Finally, back when we talked about the charge, we said that, this little dinky little charge moves through the circuit, blah, 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 blah. And then it has to slow down and it goes through the light bulb. And that causes it to give the light bulb energy. The wires, however, are so good at conducting electricity, the charges do not lose energy through it. So what's the deal? The deal is in the final property called resistance. What do I mean by resistance? Resistance is a property of matter that all conductors have. It doesn't have a definition. You're not going to define it yourself, but know this, everything has resistance. Some materials that are really good conductors have very low resistance. And if the resistance is very low, the current is very high. The charges can zoom quickly. But something like the light bulb has high resistance, which causes the current to what? To decrease, to move slowly. I want you to think of resistance like speed bumps on the road. If a car is traveling, through a road, and forgive me, this is a beautiful car, I know, futuristic, but if there are speed bumps, it slows down a bit. The more resistance a component has, the bigger the speed bump. So it essentially crashes into the wall. You lose a lot of energy to go through that speed bump, okay? So more resistance, lower current. Less resistance, higher current. The unit of measurement of resistance is called ohm. And then we have Ohm's law, which is arguably the most important equation in electricity. R equals V over I. Or my personal favorite version of it, or rearrangement of it, is V equals IR. All right? Memorize this. It's going to be very important. Yeah. When it comes to the relationship between V and I and R, if you take a look, I is equal to V over R. You need to understand something. If you increase the voltage, the current increases as well. So if this increases, this increases. Makes sense. Bigger battery, faster charges. If you increase or decrease, the resistance, the current also increases. Because less speed bumps mean faster motion or movement. So current and resistance are inversely proportional, but current and voltage are directly proportional. Voltage and current right now have no relationship, because voltage is something that you decide. I put in a battery, a 1.5 volt battery. I decide to put in a 10 ohm light bulb. So just me putting in a bigger battery doesn't change the light bulb. Both of these are factors that you control, and they affect who? The current. Keep that in mind. Voltage and current resistance don't affect each other. at least in simple circuits with just one component for now. Now, let's talk about resistance again. Resistance is affected by a few things. Temperature, for one, but we'll discuss temperature in the next section. We're assuming that temperature is constant. The second would be the length of a wire, and the third would be the cross-sectional area of a wire. What do I mean? I mean that if I have a wire of a certain length L, let's say that's, I don't know, 10 centimeters or so, and you double it, the resistance also doubles. The resistance also doubles. Because the longer the wire, obviously the more the charges have to go through that slow resistance. Same thing here, but with area. If this is the cross-sectional area of your wire, it's very small. If you think about it, it barely allows a charge to move through. But if you have something that's twice as large, hey, it doesn't just let one charge through, it can let two charges through, three charges through. Like it depends on how thick it is. So the thicker the wire is, the larger the area, the less resistance it has. It's inversely proportional. The smaller the area, the thinner the wire, the larger the resistance. Okie dokie. Very nice. By the way, I like to write this down as just as for me when I practice. R is equal to L over A. I know it should be proportional, but I just like to do this. So I remember that, oh yeah, R and L are directly proportional. R and A are inverse. Yeah. A trick that is very often used in exams is the concept of diameter. What do I mean? Let's assume for a second here, in this example that's already been solved, that you have a wire of a cross-sectional area A, and you double the area. What happens to the resistance? It decreases by a factor of 2. It gets halved. So if the resistance was 20, now it's going to be 10, because 20 divided by 2 is 10. Cool. But if I repeat the same question again, and I say, hey, you have a wire of area A and diameter D, and resistance of 20 ohms. And then you double the diameter, not double the area, you double the diameter. What's the value of the resistance? It's not going to be 10. It's going to be 5 ohms. Wait, how did I get that? Remember that the area of a circle is pi r squared or pi d squared over 4. So when you double the diameter, so when the diameter is doubled, technically the area isn't doubled. The area gets doubled squared because you didn't change the area directly, you changed the radius or you changed the diameter. And that has a square factor in there, which means the area is not 2 times larger, it's 4 times larger. So the resistance is not 2 times smaller, it's 4 times smaller. So 20 divided by 4 gives you what? 5 ohms. This is a very evil trick. Like when an examiner wants to make a question harder, like if they just want to raise the difficulty a bit, they use the word diameter instead of area. Keep that in mind. Now, how do I find the resistance of any component? I might ask you to describe an experiment to do so. So it's a very simple experiment. You get your component, whatever it is, and you connect it to a supply. Now, this could be a variable supply, like the supply itself can change, or you can have a variable resistor in there to change the voltage or the current. And you have an ammeter and a voltmeter. And you say, oh yeah, to find resistance, I need to measure measure V, which is the voltage, measure I, which is the current, and I can calculate resistance using R equals V over I. Perfect. Measure voltage, measure current, calculate the resistance. But you know what? In physics, we don't like to do things once. We like to do things multiple times. So what we do is we change the voltage. Like I said, sometimes by changing the value of the supply itself, and second, right? And second, you can change it using a variable resistor. Assume for now that you're changing the voltage directly, like you have a set of batteries or like a variable battery that you can click new values into, and you start with 0 volts, so you get 0 ampere. You can't really calculate anything there. But at 1 volt, you get half an ampere. Now you get the resistance, which is 2. And then we repeat the experiment several times. You change the voltage to 2 volts, that gives you more current. You change it to 3 volts, that gives you more current. You change it to 4, that gives you more current, and so on. And you get several values. Now, why do we do this? We do this, number one, so we can get an average, because it makes sure my results are reliable and accurate. And second, what we can also do is plot a graph of current against voltage, with voltage on the x-axis, because it's the primary thing I'm changing, and currents on the y-axis. If you plot these points, and it's a resistor, like a fixed resistor, you should get a nice straight line going through. The slope of this line, or like the inverse of the slope of this line, shows you what happens to the resistance. If the slope is constant, the resistance is also constant. Now I want to go over IV graphs of different components, meaning we put a component in that circuit, in this circuit that you see right now, over here, and we change the voltage and we get lots of readings when we plot a graph. There are 3 components that you need to remember. One, the fixed resistor, which is just a component with resistance. Something has fixed resistance. If you plot an IV graph, it ends up being a straight line, which means the resistance is what? Constant. All right. But if you put a lamp, like that first light bulb that we put up there, a filament lamp, and you start increasing the voltage, you'll notice that the current does increase. Like, let's zoom in a bit. You'll notice that the current does increase, but it doesn't stay constant for long. It actually starts decreasing in slope. The question is why? Why does it like droop down, the slope decreases? Because the higher the voltage, the brighter the light bulb gets. But light bulbs don't just get brighter, they also get hotter. So the temperature of the light bulb also increases. If a metal heats up, its resistance also increases. Which means, what do you think should happen to the current? It should decrease. But remember, you're increasing the voltage, so the voltage should increase the current, but the resistance should decrease the current. So the slope just ends up decreasing instead. Because the hotter it gets, the higher the resistance, and therefore the lower the current gets. Okay? If I ask you to sketch this, you should sketch this from memory. If I ask you to explain why this line slopes this way, oh yeah, it's because as the voltage increases, the light bulb gets brighter, and as it gets brighter, the temperature increases, and as the temperature increases, the current drops. Then finally, we have a diode. I'm kind of spoiling like the next section, but a diode is a component that allows the current to only flow in one direction. So current always flows in the direction of the arrow of the diode. But if the current tries to flow in the opposite direction, the diode stops it. So it's like a one-way gate. Current goes right, but can't go left. So if I plot an IV graph for a diode, you'll notice that just a little bit, for a small voltage, it doesn't conduct. Because diodes are not made of metals. They're made of what we call semiconductors. And it's a specific type of semiconductor that needs a little bit of extra voltage to start conducting. This voltage is around 0.5 to 0.7. It depends on the material. It's a tiny thing. But the moment the voltage crosses that value, it shoots up. Boom. It has almost no resistance, almost zero, which is why it doesn't even have a slope. No. It's almost vertical. But we do give it some slope so we can see. what's going on. The important feature here is what? Why is this line horizontal on the other side? Now, we didn't focus on that in the previous graphs because they were all symmetrical. But the left side of the graph shows you negative values of voltage and negative values of current. Negative simply means we changed direction. We changed direction. All right? And obviously in a diode, if you change the direction, it does not let the current through, so the current stays 0. That's basically it. Nothing more. Okay. You need to memorize these, all three. You should sketch them right away and identify which component the graph is trying to, show you. Final quantity, something that we call power. Now, this is honestly from unit 1, so very old quantity, nothing new, it's just old. So what is power? It's the energy per unit time, right? But here's the thing though. In a circuit, a source transfers chemical energy into electrical energy, right? But then in a component, like a light bulb, for example, it takes the electrical energy and turns it into heat or light. A resistor, for example, just gives out heat. A light bulb primarily gives out light. A speaker gives out sound, and so on. So please note that in any cell or battery, for example, you change chemical energy to electrical. But in a resistor, you change electrical energy to heat. In a light bulb, you change electrical energy to light. Now, in electricity, because we only measure voltage and current, the equation to calculate power is not P equals E over T. It's actually P equals IV, or V times I, voltage times current. Okay? But what if I want energy? What if I want energy? Now, energy is power times time. Back from unit 1. And power in electricity is IV, or VI, times T, which means energy in electricity can be calculated using VIT, or IVT. Okay? I have a very bad pun I'm holding back. Do you guys want to know the pun? Oh, well, I'll hold back. I'll hold back. Yes? Uh, why is it that when you're feeling down or tired, doctors always want to give you vitamins? Because VIT gives you energy. Anyway, I'm sorry. Don't log off now. Okay, let's keep going. Let's keep going. I'm sorry. Now, we have other versions of this power equations. And we have other versions. P equals I squared R. People are dying now. And P equals V squared over R. Now, where did these come from? P equals I squared R is actually P equals VI. And I replaced the V with IR. So you end up with IIR, which is I squared R. P equals V squared over R is actually P equals VI again, but I equals V over R. Back from Ohm's law, it's the same thing. So I replaced the I with V over R, and I end up with VV over R, which is V squared over R. These formulas are useful if I give you I and R and ask you to get P right away. But honestly, if you forget them, that's fine. Because if you haven't noticed, both of them use the same two formulas, P equals VI and V equals IR. If you memorize these two, you can solve any formula involving I and R, or I and V and I, and P and R, and whatever. Okay? However, this version of the formula, I squared R, will be very useful later in magnetism when we talk about power lost or dissipated as heat in a transformer, or when we transmit electricity. Yeah. Let's talk about something new, essentially. We haven't seen this a lot before because it wasn't there for a long time in the syllabus. What is a kilowatt hour? Now you're like, what? I've never seen that. A kilowatt hour is a unit of energy that we use at home. It's the amount of energy consumed by 1000 watts of power in 1 hour. What do I mean by that? Let's say I open up my application to pay my, electricity bill this month, and I pull it up. It's like, oh, what do you mean I need to pay £1,000? Like, "Yeah, it's not, thank God. But let's say I have to pay £1,000. How does the electricity company measure the electrical energy that I use? It has that electricity meter, right? Like right next to your door, somewhere near your apartment. Uh, but an electricity meter doesn't measure energy in joules because joules is actually a very small unit of energy. We measure it in kilowatt hours, meaning how much energy would 1000 watts of power, like a kettle, for example, my kettle here at home has a power rating of 1000 watts. My vacuum cleaner is 1500 watts. All right. Every device has a certain wattage. My charger, my phone charger, is like 20 watts, sometimes 30 watts. Depends on if it's a high-speed charger or not. And then I just multiply it by 1 hour. Because isn't energy power times time? Kilowatt is power, hour is time, so you end up with kilowatt hours. Because the values of energy that we consume at home are super duper large, we can't use joules. Okay, so what is a kilowatt hour? It is how much energy is used by 1 kilowatt or 1000 watt in 1 hour. How do I get the value in joules? Like if I tell you, this month I used up 37 kilowatt hours, for example. That's nothing, but let's say I used 37 kilowatt hours. How do I change that to joules? Remember, energy is power times time. This is 37 times kilo means times 1000, because that's the kilo, times what's 1 hour in seconds? 60 times 60. This gives me the answer in what? In joules. Let me work it out. So 37 times 1000 times 60 times 60. It's a giant value, so standard form, 1.33 10 to the power of 8. The 3600 in this revision sheet is the time of 1 hour, but times 60 times 60. This is extremely new to the syllabus. We've never used this before. So, and even in 2023 up to 2024 now, like this year's 2025, we haven't seen it much yet. Like maybe once. Okay. So we're going to see that now. Okay. Now, let's solve a few questions. Define potential difference. Potential difference or voltage or EMF, it doesn't matter. It's the same thing. It's the amount of energy transferred or work done per unit charge, but add one little extra bit. If it's EMF, it's by a source. To drive a charge per charge by a source through the whole circuit. If it's potential difference, it's work done per unit charge through a component or lost through a component. All right. Sometimes these definitions want you to mention the energy change that has happened, by the way. It honestly depends on how many marks the question is, but it also wants you to mention the energy change. So here's the question. Potential difference is the energy change from what to what? And you don't have to be specific. I'm looking for in general. Hmm. Is the energy change from electrical to something else, like thermal or light or something? So keep in mind, if I ask you to define potential difference, and I ask you to also include, in terms of energy, explain it in terms of energy, you have to mention the energy types from electric to other forms. Okay? Next. State the equation which defines EMF. So what's EMF? E equals W over Q, or you can say work per unit charge. Just write it down as an equation. Next. EMF of a battery is 9 volts. The battery is in a circuit. Calculate the work done by the battery when it moves a charge of 30 coulombs. So this one's easy. Work is EMF times Q. So 9 volts times 30 coulombs, which gives me 270. Yes, 270. This one's easy. Direct, to the point. Moving on. An electric heater uses a resistance wire of resistance 26 ohms. The power dissipated, meaning lost, so power dissipated means power lost, in the resistance wire is what? Oh, wait. I hate it when a notification just pops up. Okay. The power dissipated in the resistance wire is 2,500 watts. Calculate the current in the resistance wire. So how do I calculate current? Look at what you have. Do not automatically go for V equals IR. I have power, and I have resistance, and I want current. Short way is to use P equals I squared R, which means I squared is equal to P over R. And then I have to square root my answer. So square root 2,500 over 26, which gives me 9.81. Hey, almost like the value of G, right? Gravity does. Or if you forget this version, you can say, oh yeah, P equals VI, so I equals P over V, but I don't have V. So first, you get V equals IR separately, right? Oh, sorry, my bad. We want the current, right? What do we have? Power and resistance. So what can I get? You can say P equals IV, or I equals P over V. You have power, but you don't have this. So you say V equals IR. Now you don't have I again. You don't have I. But you can say that I times 26 is your V. And plug that in here. So it's 2,500 over I times 26. Which gives you I squared equals 2,500 over 26. You can do that, or you can memorize all the equations and choose the easiest one. So 9.81 ampere. Next. The resistance of a wire, the resistance wire of a heater has a length of 1.2 meters. So this is the length. An area, oh, thank God he used the area, of 7.9, 10 to the power of -7. By the way, this is a challenging question, okay? A new heater is designed using wire of the same material with a length of 1.8. Ooh, the length what? Increased. And a cross-sectional area of 5.8. Oh, and the area what? Decreased. Calculate the resistance of this wire. Well, what was the resistance of the old wire? 26. So the first wire was 26 ohms. So what's the new resistance? Well, first, remember, resistance is proportional to length and inversely proportional to area. If the length increases, resistance should increase. By how much? Again, this is a challenging question. By how much? So first, I want to see how much the length increased by. The increase in length is 1.8 over 1.2. It's a ratio. 1.8 divided by 1.2, which gives me 1.5 times. So the length is 1.5 times larger. So the resistance will also be 1.5 times larger. What about the area? How much did the area decrease by? What's the ratio? What's the change in the area? What's the change in the area? It's 5.8, because that's the new area. 10 power negative 7 over 7.9, the old area. I just want to see how many times this is, larger or small. So this is 0.734 times smaller. So what's the value of the new resistance? Okay, the old resistance was 26. The length increased 1.5 times, so it increases by 1.5 times. This is because of the length. Then the area decreased by 0.73, right? Decreased by 0.73. So we divide, not times, by 0.73. That's your area. Look at this. I take the old resistance multiplied by whatever the length has changed by and divided by whatever the area has changed by. You just do the opposite. Everything will fix itself. So 26 times 1.5 divided by 0.734. This gives me a 53.1 ohm resistance. This is not an easy question. It's actually quite challenging because you need to see how much it gets multiplied by, increased or decreased or whatnot. Okay. We decrease the area, right? But because resistance and area are inversely proportional, whatever I do, it'll be the opposite. You know what you could have done earlier? You could have just did the opposite ratio. So instead of dividing, if you want to multiply, you do the opposite ratio. But the reason I did this is to keep, my thought process the same. What's the change in area? It's 0.7 times smaller. So how does the resistance change? Is it multiplied by 0.7 times? No, it's inverse, so it's divided. Okay. Next. A 2,500 watt heater is used in a country where electricity costs $0.3 per kilowatt hour. Calculate the cost of using the heater for 2 days. Okay. How do I get the cost? Well, he said it costs $0.3 per kilowatt hour, which means I need the number of kilowatt hours. But I have power and time. So what do I do first? Step one, let's get the energy, which is power times time. So 2,500 times 2 days. I can't use days. It has to be in, seconds, right? Or if you think about it, in hours. Because I want the power to be in kilowatts and the time to be in hours. So look at how I'm changing this. This is the power, and this is the time. I don't want it in watts and days. I want this in kilowatts. So this is going to be 2.5 kilowatts times 2 days is how many hours? 2 times 24, 48 hours. Which gives me 2.5 times 2 times 24, 120 kilowatt hours. Now we have the energy in kilowatt hours. Number two, you need to get the cost. If 1 kilowatt hour is $0.3, then 120 kilowatt hours is how many dollars? Dollars. 36. You pay $36 because you kept your heater on continuously for 2 days. Who does that? Who does that? Okay. Next. A wire has a uniform cross-sectional area. Which statement is correct? Okay, let's read. The resistance of the wire is directly proportional to its cross-sectional area. What? No. It's inversely proportional to the area, so no. The resistance of a wire is directly proportional to cross-sectional area. Oh yeah, that's the same thing. No. The resistance of a wire is directly proportional to the length. Yes. And inversely proportional to the area. Yes. That was probably C. Well, let's read the last one. The resistance is directly proportional to length and inversely proportional to diameter. Nuh-uh. But you may say, but it's inversely proportional to area. Yeah, but area is equal to pi d squared over 4. If he said to its diameter squared, he would be right. But it's not inversely proportional to the diameter. Inversely proportional to diameter squared. So C is still the correct answer. Next. The diagram shows the current voltage graph for a metal wire. What can be deduced from the graph? Like, what can we find out from the graph? As the voltage increases, wait a second. Before I keep going, isn't this a straight line? Straight line means it's a fixed resistor. This means the resistance is constant. Before I even start, and the temperature is constant, nothing is changing. Because the voltage and current are increasing uniformly with each other. So as the voltage increases, the temperature increases? No. As the voltage increases, the temperature decreases? No. As the voltage increases, the resistance increases? No. As the voltage increases, the resistance remains constant? Yes. That's what I want. I didn't even need the term as the voltage increases. Resistance is constant. Moving on. Yeah. Next question. A battery is connected to a circuit. It's switched on for 1 minute. During that time, there is a current of 0.4 ampere. So hold on, I have the time and I have the current. The battery supplies a total of 48 joules. I have the energy. Which row gives the charge and the EMF of the battery? So I want charge, which is Q, and EMF, which is V, which is voltage. Now, when it comes to Q, what do I have? I have time and I have current. Oh, that's all I need. Current is charge over time, which means charge is current times time. Current is 0.4 and the time is 1 minute. I can't use minutes, right? Because the term charge or current is ampere, which is charge per second. So it's times 60, not times 1. So 0.4 times 60, this gives me 24 coulombs. So the answer is either C or D. Good. The EMF of the battery. Now, here you have a few options. You have energy. So option 1 is to use the definition of voltage, which is energy per charge or work per unit charge. And since we already got the charge from the previous step, you can say it's 48 over 24, which gives you 2 volts. Or you have energy and current, and you want voltage, and you have time, so you can use E equals VIT, which means V is equal to E over IT, which is 48 over 0.4 times 60 again. It's the same answer, too. So the answer is C. Both options are okay. Very nice. Next. Oh, yeah. Time for the good stuff. Let's talk about circuits. But these were circuits. Yeah. Let's talk about bigger circuits. Let's first talk about all of these components. Now, you don't have to memorize them perfectly 100%. It's good that you remember what they look like, but you don't have to memorize them all, okay? Okay. So as I was saying, you don't need to memorize the components. Not all of them, not 100%. But it's good to know most of the basic ones. There's a lot more than these. Lots more. But at least these are some of the basic ones that you'll see very frequently. So starting from the top left hand, the cell and the battery are basically the same thing. A battery is just multiple cells. Long line is positive, short line is negative. Positive and negative. Switch is always drawn open because a closed switch is just a line. Power supply. This could mean anything. This could be like a battery. It could be a battery pack full of batteries that gives you a voltage. It could be your computer's ATX power supply that controls and gives you different voltages. Regardless, it's just two circles. And either it could be variable with an arrow through it or not. It doesn't matter. An AC power supply means a socket. It's the same symbol as a power supply with an AC wave in the middle. Voltmeters and ammeters, you know the drill. You know what a diode is. A light emitting diode is a diode that emits light. So we just draw the diode and two light rays out of it. A light bulb is a circle with an X. A fixed resistor is a rectangle. A variable resistor is a rectangle with an arrow. A potential divider is a resistor with an arrow but it's coming from the outside. We'll see the difference near the end of the session. A thermistor is a resistor that changes based on temperature. So this is basically a thermometer that's placed in it. An LDR is a resistor that changes based on light. So you have light rays coming in to hit it. A heater is like a resistor, but with more resistance and more heat. So we just draw a few lines in the middle. A buzzer is something that produces sound. All right. A bell also produces sound. They both basically have the same symbol. It's like a half circle. Doesn't matter which side is up. And a fuse is a safety feature that we'll discuss. It's like a resistor in terms of the symbol, but there's a line in the middle to represent the wire inside. We will see these often, okay? Let's describe some of these in more detail. First, a variable resistor. It's a resistor whose resistance can change. You change the resistance of a variable resistor by changing the length. Now, the way it works, and if we zoom in here, this is the structure of it. You have a long resistor wire that is connected to one side of the battery, but the other side is not. The wire itself is connected to what we call a sliding contact. It's like a clip that clips on, and you can move it back and forth and slide it back and forth. This length is the effective length that affects the resistance. The longer this length becomes by moving the slider to the right, the greater the resistance. The smaller this length, the lower the resistance. So if you move it to the left, the resistance decreases. If you move it to the right, the resistance increases. Okay. Now the reason for that, if you're curious, is because as the current moves from positive to negative, it only passes through this section of the wire, and then it goes out. So if this entire wire was 100 ohms, and it passes only through half of the length, then it's actually passed through how many ohms? 50. You can always get the value of the resistance by checking the ratio of the lengths. Like, are you through half of it, a quarter of it, a tenth of it, 3/4, and so on. Is this concept used for light switches where you control the brightness? Yes, absolutely. But we'll see that light switch control thing in the end, because that's actually a potential divider. But it does use a variable resistor in it. Okay. Now, the purpose of it is to control the current. Next, what's a thermistor? From its name, it's a therm resistor. Depends on heat. If the temperature of a thermistor increases, its resistance decreases. It doesn't increase like the light bulb, because thermistors are made of what we call semiconductors. They're not metallic conductors, all right? Metals, when they heat up, sure, their resistance does increase, that's true. But non-metallic conductors, which are called semiconductors, are basically silicon and doped with boron and nitride. They're non-metallic conductors. When they gain energy, usually in the form of heat in this case, they get more free-moving electrons. They become better conductors, which means they resist less. And when they cool down, they lose that energy. They lose those free-moving electrons. They go back to their atoms. So the resistance increases. So the temperature and resistance are inversely proportional. So be careful. If it's a metal, when the temperature increases, the resistance increases. When it's a non-metal, a thermistor is the only non-metal we'll care about for now. When the temperature increases, the resistance decreases. Its cousin, or its brother from another mother, is the LDR. It basically is a resistor that's affected by light, basically. When the light shining on that resistor increases, its resistance decreases as well. It's inversely proportional. And when the light on it decreases, meaning you put it in the dark, its resistance increases. For the exact same reasons as what? As a thermistor. It's made of a non-metallic conductor. So when it gains energy, doesn't get hot, gains energy from the light, sunlight, light bulb, doesn't matter. It gets more free moving electrons and it becomes a better conductor, its resistance decreases. Yeah. If I plot a graph of how the resistance changes with temperature or light, this is how we sketch it. This is how we sketch anything that's inversely proportional. Not a straight line going down, but a curve with a negative slope, okay? A curve. Finally, the diode. What is a diode? We described this earlier. It is a component that only allows the current to flow in one direction. Meaning, if you take a look at this here, the current flows from positive to negative. If the current is going to flow in the direction of the diode, it passes through. Lights up the circuit as if it's not there, has no resistance. But if you connect the diode in reverse, and if the current is going to flow in the opposite direction, it doesn't even leave the supply. Again, because some students think this. Look at this. It does not go through the circuit. The charges don't go through the circuit, meet a diode, and go like, oh, there's a diode in reverse. We need to stop now. No. There's no current in the first place. There's no current in the first place. Zero current. Diode stops. Now, a diode has primarily one function, to convert AC to DC. And there are two ways to do it. The lazy way, which is called the half-wave rectifier method, okay, which basically means you take the normal AC that you're used to, alternating current, and you pass it through one diode. When the current flows this way, it goes through, yay. And when the current tries to go in the opposite direction, it doesn't, because that would make it reverse compared to the diode. So it doesn't go through, zero. But this is a very lazy way of doing it because you've essentially gotten a pair of scissors and you cut out half of your energy. You only allowed one side to go through, but not the other. The negative doesn't go through. So how do we fix this? If we want to purely convert AC to DC, we use what is called a full wave rectifier or a bridge. It is essentially 4 diodes connected in a diamond pattern. 2 of them look up and they're parallel to each other, and 2 of them look down when they're also parallel to each other. 2 of them look up and 2 of them look down. You do not have to memorize this, by the way, but you do have to know if a diode is drawn correctly or a bridge is drawn correctly or not. Remember what I'm saying. 2 of them are parallel to each other looking down, 2 of them are looking up. I don't care which is up and down though. Like these could be the ones up, so these have to be the ones down. But if I draw the diodes like this, like each one is in a different direction, this is wrong. So that's the first thing you need to identify. The second is knowing how to trace the current through a diode, like knowing how to draw how the current's flowing through the diodes. You don't have to, like I said, memorize the diagram, but you have to look at how it goes through. So I'm going to draw 2 currents, one in red when the top side of the supply is positive and the bottom is negative, and one in blue, which is when the top is negative and the bottom is positive, like when the current flips. And look how it reaches the other side, like the other terminal. So let's start with the red. Current goes up, goes right, goes down, reaches a junction. It cannot go left, so it goes right, reaches the next junction. It cannot go left, so it goes right. So this side is positive and this side is negative, and the current goes through, no problem. If you want to see the current going back, this is how it goes back. Okay. How about the blue side? Let's follow the blue line. Now the blue means the bottom terminal is positive. So it goes down, goes to the right, reaches a junction, left or right. Left is blocked off. So it goes right through D2. Then it meets the next junction, left or right. Left is completely blocked off. So it goes right. Oh, this is still positive. So what reaches the output, this is negative. So flows this way on the way back. When it reaches the negative, it flips. You essentially take the negative version of this graph and you flip it. That's all we do. This is called a full wave rectifier. So again, if I tell you you only use one diode, it's a jump and a zero, a jump and a zero. If you use a full wave rectifier for diodes, it's jump, 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 no negatives, no zeros. Finally, what is an LED or a light emitting diode? It's just a diode that shines bright, gives out light when a current goes through it. That's it. So it's basically a diode, but it's got the extra function of glowing or like emitting light. Let's get into the highlight of this particular chapter. Series and parallel connections. This is the part that confuses some people and gives them trouble. But you need to remember something. Whatever I say in series will be the opposite of what happens in parallel. All right? And then you need to memorize exactly what happens to the current, the resistance, and the voltage. The current, the resistance, and the voltage. Sometimes it increases, sometimes it decreases. Sometimes it splits, sometimes it doesn't. Sometimes it's the same, sometimes it's not. Like, you need to memorize how each method of connecting components together changes these three factors. So starting off with series connections. A series connection means you connect the two resistors along the same wire. So if I were to connect them to, let's say, a 10-volt supply, and there's a current I going through it, so number one, the current is the same. You have the same current going through both because it's only one wire. That's the current. Second, when you connect resistors in series, their combined resistance increases. And you calculate it using R1 plus R2 plus R3 plus, you just add them. So if this was 10 ohms and 10 ohms, the total would be 20 ohms. Finally, but most importantly, what happens to the voltage? The voltage of the supply in series gets split. Now, the voltage of the supply doesn't change, but the voltage that you try to deliver gets split. The potential difference splits. If I were to calculate the voltage across the first resistor, I would first need to get the current. So I'd say I equals V over R, which is 10 over 20. That's the total voltage and the total resistance, which is 0.5 amperes. And then if I ask you to get the voltage only across the first resistor, V1, you would say IR1, which is 0.5, that's the current, times 10, which is 5. This means that this resistor only gets 5 volts from the supply, which means the other one also gets 5 volts from the supply. The voltage, the total voltage that you have, gets split, gets divided. It's not always equal. It depends on the ratio of the resistors. For example, if this wasn't 10 and 10, what if this was a, let me delete all of this. What if this was a, let's just use the same supply, a 10 ohm resistor and a 90 ohm resistor, going for the extreme. The first resistor will only get 1 volt and the second resistor only gets 9 gets the rest because the voltage gets split according to the ratio of the resistors. One will increase, the other has to decrease so that the total voltage stays the same. It's 10 volts. Okay. That's if they're in series. What if the resistors are in parallel? Well, everything I said gets flipped over. Huh. In series, I said the current is the same, like it doesn't change, right? But in parallel, you have two branches for the current to go through. It's not just one loop, it's two loops actually. So the current that flows through the circuit splits. Does that mean it gets smaller? On the contrary, the combined resistance of resistors in parallel doesn't increase, it actually decreases. Because if you think about it, connecting resistors in parallel on top of each other is like making a wire thicker. You allow more charges to go through at the same time. So connecting resistors in parallel gives the charges more space to go through, which increases the current. So the current gets very large and the resistance A decreases. How do we calculate it? Using this rule. R equals product over sum, or R1 times R2 over R1 plus R2. So for example, if this was 10 ohms and 10 ohms, their combined resistance wouldn't be 20. It would be 10 times 10 over 10 plus 10, which gives me 5. The combined resistance of resistors in parallel decreases. And it has to be lower than the smallest resistor. So if I have 10 and 10, it has to be less than 10. If I have 10 and 20, still less than 10. If I have 10 ohms and 2 ohms, it has to be less than 2 ohms. The resistance just decreases, drops hard. Finally, this is also, voltage is arguably very important. Why? Because in series, if you remember, the voltage gets split. In parallel, it doesn't. In parallel, all the components get the same voltage. This means that this 10-volt supply can deliver 10 volts completely to the first resistor and 10 volts completely to the second. Everything in parallel gets the same voltage. And that's because each resistor gets its own charge. Like this is a charge carrying 10 volts, goes through just this. Here's another charge carrying another 10 volts. It only goes through R2. In series, the same poor charge has to do what? If you had a charge carrying 10 volts, oh, it has to go through both R1 and R2. So it's forced to split its voltage. But in parallel, each one gets its own voltage because it gets its own charge, full voltage. Very good. Now, obviously, parallel has a few advantages over series. What do I mean? At home, most of your light bulbs and switches and sockets are all connected in parallel for 3 reasons. Number one, everything in parallel gets the full voltage. So at home, if my voltage is 220 volts, this light bulb gets 220, this light bulb gets 220, this light bulb also gets 220. Everything lights up bright. Sure, you end up paying more money. Capitalism. But that sounded Scottish. Yeah. Everything gets the same voltage. But here's another advantage. You can switch them on and off separately or independently. Meaning you can close the switch here and open this switch and close this switch, and you have 2 light bulbs on, 1 light bulb off. It's up to you. And then if one of them breaks, the others still work. That's the advantage of parallel, like having them on separate branches. They don't affect each other. If everything in your house was connected in series, If everything in your house is connected in series, if one light bulb breaks, everything goes off. Everything turns off. Okay. However, there is something else that we do connect in series. It's very important. Cells or batteries. You can have more than one cell in series, by the way. Like if I put a 6-volt cell in this example next to a 3-volt cell, the voltage that you deliver is not 6 or 3, it's 9. They get added up. So when you connect cells in series, you just add their voltages together. To anybody observant, you look to the right side over here and say, why is this 4 volts, not like 8 or something? Why is it 4, not 8? Because look at this first cell, its positive and negative are pointing to the left, so the current is going to flow to the left. The second cell's positive and negative point to the right, which means it's in the opposite direction. These are in the same direction. These both try to push the current in the same direction. So what do? They cancel out. Instead of adding them, you subtract them. So if the cells are in the same direction, you add them. If the cells are in opposite direction, you subtract them. Yeah. Can you put an AC supply next to a battery? I mean, you can. It's not a good idea, though. Finally, let's talk about the potential divider. A potential divider is just a very fancy way of saying two resistors in series. But the function here is to actually split the voltage. Like, look at this example. If this was a 10 ohm and this is a 30 ohm resistor, the voltage will split with a ratio of 1 to 3. So 2.5 volts to 7.5 volts. Do you know what that means? This means if you connect another light bulb only parallel to the first resistor, it gets 2.5 volts. You get to choose what the voltage is across it. No. But what if I connect another light bulb here? This will get what? 7.5 volts. Because the voltage was split first according to the ratio of the resistors, and then you ended up connecting this component not parallel to the entire circuit, but parallel only to the first resistor. So it only gets the voltage of the first resistor. If you take a look at the second one, you connect it parallel to the second resistor, so it only gets the voltage of the second resistor. So if I were to turn this circuit on, the light bulb on the right would be bright and the one on the left would be dim. A very similar circuit to this is what we call a variable potential divider. This is a much cleaner version because if I wanted to change the voltage, like increase and decrease the voltage directly, I don't need a potential divider with 2 resistors and then I have to split the voltage. And then if I want to change the ratio, I have to change the ratio of the resistors. I can just connect a variable resistor completely to the supply, which means this entire wire gets the full 10 volts. But then you connect your slider or sliding contact in parallel to the light bulb that you want. So if the sliding contact is in the middle, it's not parallel to the full wire. It's parallel to what? Half of it. So it doesn't get 10 volts. The entire wire gets 10, sure. But if you're only connected to half of it, you get what? 5 volts. What if you move this parallel here to the very end? You get the full 10 volts because you're now parallel to the entire wire. What if you move it to the left? You get nothing because you're parallel to nothing. Look, you're parallel to an empty wire, like it's nothing. This is called the variable potential divider. And whoever asked me earlier, is this how light bulbs or like variable light bulbs that you have at home work? This is how they work. A variable potential divider is so much cleaner than just putting a variable resistor in series with a light bulb. Put it in parallel instead. This allows you to change the voltage directly from 0 to full to 10 volts. 0 being the slider near the side that's connected to the battery, and the maximum being the other side, the other end. Okay? So the purpose of it isn't to control current now. It's to control what? Voltage across the component. As one final rule, a variable potential divider can follow this rule. V1 over V2 equals R1 over R2, meaning the ratio of the voltage is the same as the ratio of the resistors. We sometimes use this when solving questions. It does help. Do I always need it? Not really, but it does help. Okay. Let's solve a few questions. Starting off with this March question over here. A circuit consists of a DC supply, a lamp, and a thermistor. Draw a circuit diagram of these components connected in series. So let's go. A DC supply. You can either draw just the supply and just write DC on it, or like positive and negative, or you can draw a battery or a cell. That's fine. A lamp, so light bulb, and a thermistor are all in series. Do I need anything else? Nope. That's it. Okay. Next. Explain what happens in the circuit you have drawn when the temperature of the thermistor increases. Okay. When the temperature increases, the resistance of the thermistor decreases. And if the resistance of the thermistor decreases, the current will increase. But there's a light bulb in there. So the light bulb becomes what? Brighter. Look at the way I sequenced my logic. I started off with what happens when the temperature increases? When the temperature increases, the resistance decreases of the thermistor. Like I'll be even on of the thermistor. But that causes what? That causes the resistance of the circuit to decrease. The total resistance decreases. And the total current increases. Right? So the current increases. That's honestly enough. Honestly, that's enough. But you know what? I just want to push through. So the light bulb is bright or glows bright. It's only 2 marks. So honestly, I'm just looking for resistance decreases so the current increases. That's genuinely what I'm looking for. But I wanted to express exactly what's happening inside. Because if it was worth more marks, that's great. We end up getting more marks. Next question. Ooh, I see an AC supply. Oh, what's this? Huh? Is this a single diode or a full wave rectifier? Like without even reading the question, is this a single diode or a full wave rectifier? Just one diode. Like, look at this. He has the AC supply connected to one diode, and he's like, what's the voltage across this resistor? If it was the full wave rectifier, it would be a bunny hop going up, down, even if it's negative. But it's not. It's just one diode. So it's C. Cuts off half of the voltage. Next. Figure 7.1 shows a circuit that contains a battery, a switch, and a voltmeter, and 340 ohm resistors. Oh, this is important. He didn't draw the values. He just mentioned them here. They're all 40 ohm resistors. R1 and R2 and R3. Describe, the switch is opened and R1, R2 form a potential divider. Explain what is meant by the term potential divider. So what is a potential divider? Now, the function of a potential divider is to do what? Is to split the voltage or divide the voltage between two resistors, right? proportional to the ratio, depending on the ratio. That is what a potential divider is, and that's the function of it at the same time. So a potential divider is just what? A circuit that divides the voltage across two resistors in series according to their ratio, or according to the value of the resistance, or proportional to their values. Next up. Remember, all of this, and the switch is still what? Open, which means this is open, which means R3 is not part of the circuit yet. Because the current's going to flow here through R1 and R2 and then come back. It's not going through R3 yet. The reading on the voltmeter is 7.5, which means this is 7.5 volts. What is the EMF of the battery? Ooh. Actually, that's easy. Didn't he say they're all 40 ohm resistors? Like this is 40, this is 40, this is 40. No, but this doesn't count. If I have two resistors that are equal in value in series, doesn't the voltage split equally between them? Doesn't the voltage split equally between them? So if this gets 7.5, this also gets what? 7.5. Which means the total voltage is what? 15. 7.5 plus 7.5 is 15. I could tell all of that just because he said, hey, they're all 40 ohm resistors, which means they're all the same resistance. Okay? Which means the voltage splits equally. So if the first one got 7.5, the second one gets 7.5. If the first one got like 200 volts, the second should also get 200 volts. However, now the switch is closed. Oh boy. What's the resistance of the complete circuit? Yeah, I'm going to redraw the circuit here, but instead of vertically, because sometimes mentally in your head it's hard to imagine, I'll draw it horizontally. Like I'm just going to rotate this 90 degrees. Here's R1, and then there's R2, and then like R3 is above that. Which means what? Which means you have two resistors in parallel first, which are then in series with this dude over here. So step one, I need to get these two together first in parallel. And after I get their combined resistance, I add it to the series one. So let's go. The parallel version first, it's product over sum, R1 times R2 over R1 plus R2, which is 40 times 40 over 40 plus 40. This will give me 20. And this is something you can memorize, by the way. If you have two resistors in parallel and they have the same value, their combined resistance is half of them. So 40 and 40 give you 20. 30 and 30 give you 15. 5 and 5 gives you 2.5. But then I need to add it to the series resistor. So the 20 ohms, the combined 40 and 40 gives you 20, plus the 40 for that separate resistor. This gives you a total of 60 ohms. Knowing what to sequence and when is important. Calculate the reading on the voltmeter when the switch is now closed. Ooh. Oh, wait. Hold on. Let me erase this. Too bad. Or maybe I didn't need to. Oh, yeah, I didn't need to. Didn't we just say that these two together are worth 20 ohms? And now it's technically in series with this, which is 40 ohms. Will the 15 volts of the supply now split equally? No, it won't. R1, which is 40, will get more than R2. R1, which is the 40 ohms, will get more than R2 and R3 because they're together, they're 20 ohms. So when he asks you for the reading on the voltmeter, he means what's the voltage across this now that this is 40 and 20? It's going to be what? 10 volts. And you can use two methods to get this. You can either use Ohm's law, which is V equals IR. Let's try that one out first. Or you can use the ratio example. Remember how I used ratios? R1 over R2, V1 over V2? Let's try this out. Let's try Ohm's law first. Step one, I need the current. So I equals V over R. The total voltage is 15 volts. So the total resistance is what? 60. Oh, wait, I didn't write this. Okay. 60. This gives me a current of 4.25. Then you use Ohm's law again, but that's to get the voltage of V1, which is the voltage across R1. So it's 0.25 times 40, which gives you what? 10. Yay. Or you can use the ratio example. But ratio of what exactly? I don't have V2. Like, I don't know what this voltage is, but I do have the total voltage. So here's another version of this ratio example thing. You can say V1 over V total equals R1 over R total. It still works if you compare it to the total, not just to the one next to it. So V1 over, what's the total voltage? 15 equals R1, which is the 40 ohms that you want, over the total resistance, which is 60. So V1 is equal to 40 over 60 times 15. This gives you 10. Pick your poison. Doesn't matter. They're both okay. They're both okay. All right. Next question. Oh, wait. Do you want to take a picture of this? Why did it disappear? Okay, the app's being weird. Okay, never mind. You can go back and pause and get the picture there. Next question. I see three cells in series. I see R1 and R2 and a diode and R3 and a voltmeter. The three cells have zero resistance. R1, R2, R3 are identical, meaning they're the same. The reading on the voltmeter is 6. The voltmeter reading is parallel to all three, which means the total voltage or EMF here is 6 volts. When the diode is conducting, it has zero resistance and zero potential difference across it. He's just saying the diode doesn't affect anything yet. Determine the EMF of one cell. If three cells have 6 volts, this means one cell has what? 2 volts. Because 2 plus 2 plus 2 gives you 6. Then, determine the ratio of the potential difference across R2 to the potential difference across R3. That's a slightly challenging question. It's actually hard, but it's based on what we just did earlier. Remember? If this is R1 and this is R2, and this is now R3, which is in series to it, just like the previous 40, 40, 40. When he says, hey, what is the ratio of the voltage of R2 to R3? Sorry, this is R2. I don't know why I wrote that as R3, and this is R3. How is the voltage going to get split? Now, you might say, I don't have values. That's fine. Assume anything. Assume anything. If this is 10 ohms and 10 ohms and 10 ohms, what's the combined resistance of R1 to R2? R1 and R2? 5. Which means this is technically 5 to 10. And what does he want? He wants the ratio of the voltage. The ratio of the voltage is the ratio of the current. So 5 to 10 is 1 to 2. So you can say it's 1 to 2. Or 0.5, that's fine too. It's not an easy question to get. It needs you to have seen questions like this before. And the fact that I can just get two resistors that are identical, it's half the voltage. So this gets half, this gets 1, and then it splits. What's the ratio? 1 to 2. Next. All the cells are reversed, meaning the current now wants to flow this way. Wait, if the current wants to flow this way, It cannot flow through R1 anymore because the diode stops it. So the current's only flowing through R3 and R2, which are now technically in what? In series. R1 doesn't exist now because the current can't go through it. The current can't go through it, right? Hey, wait a second. If R1 goes away, what happens to the total resistance? It was in parallel, now it's only in series. Remember, when we added things in parallel, the resistance would decrease. If you remove the parallel portion, the resistance will what? Decrease. Sorry, increase. The resistance increases. You know, because you lost that parallel connection. It's now just series. So the current decreases. That's very sad. Then finally determine the new ratio of the voltage of R2 to R3. Now this one should be easy. If you only have R2 and R3 in parallel, in series, sorry, and they're both the same resistance, the voltage will be split what? Equally. Which as a ratio means it's what? 1 to 1. It splits the voltage equally. So what's the new ratio? 1 to 1. Okay? This was a tough question, by the way. Like using ratios and concepts, it's a tough question. And I picked it on purpose. The final part of this unit, or at least this section of electricity, and we're done. Let's talk about safety. Now, obviously, electricity can kill us. How? Well, it can give us an electric shock. That's bad. And it can set us on fire. Not us directly, but can set everything else on fire. Like, okay? Can set everything else on fire. So in order to keep ourselves safe, we need a few basic things at home, like insulating wires, using a fuse, and so on. So let's first take a look at what's the electricity at home like. An electric socket or electricity at home is called mains electricity or a main circuit. It consists of two main wires and a third safety feature. The two main wires are the live wire and the neutral wire. There are no positive and negative wires. Why? Because electricity at home is always set to 220 volts AC. Electricity at home is 220, sometimes 240, like it fluctuates a little bit, but it's AC, which means it doesn't have a positive or a negative. The live wire is the super high voltage wire that's always fluctuating, and the neutral wire is just there to complete the circuit. This is usually at 0 volts. This means that if I get a piece of metal and I shove it into just one of these openings in the socket, if I shove it into the live wire, I'm a cooked goose. And if I shove it into the neutral wire, I'm A-okay. You and your luck. I don't know which one is live and neutral. We never label them. Electricians and designers never label these. It depends on who connects the wires in the walls. Now, the earth wire is actually a safety feature. Not all countries have this. This is a safety feature that protects you from getting electrically shocked if a metal case becomes live. But I'll discuss this over here. Like we'll talk about the earth wire down here. So as I said, what are the hazards? You can get electrically shocked or you can cause an electric fire. What causes these things? Insulation, if it's damaged. If you overheat the cables, because that damages the insulation, because if wires get too hot, it could melt the insulation and it could catch on fire. Damp conditions means if it's wet. Obviously, you don't charge your phone in the bathroom. If you do, something's wrong with you. Too much current, because too much current will cause the cables and the sockets to overheat, which causes what? Electric fires. Okay? So what safety features do we have at home to protect us from these two main problems? Too much current is the reason why things overheat or things burn and like, sockets get damaged and everything else. And to protect you from that, we have a fuse. A fuse is just a very thin wire, by the way, very thin wire that's always placed on the live side of a circuit. This wire is designed to melt if the current gets too high. So let's say, for example, you have a 5 ampere lamp. It uses 5 amperes normally. And you close the switch and it draws in 5 amperes. That's great. It's going to work fine. But if the current increases, it'll burn. Like the lamp will burn out. Replace the lamp with any device you want, okay? So what we do is we put a fuse over here. A fuse has a rating. Let's say 6 amperes. Meaning if the current reaches 6 amperes, it will melt. And when I say melt, I don't want you to imagine it slowly melting away. No, it just pops right away. Just snaps, breaks immediately. Okay? So when you close the switch and the current that's flowing through is less than 6 amperes, like the normal 5, no problem. Fuse is like a wire, no problem. But if you close the switch and for some reason, maybe there's an electric surge, maybe somebody's fooled around with the switches at home or the wires, whatever it is, and the current increases for any reason, it goes through what first? The fuse. And it melts the fuse. It just like pops it. So now there is no current that reaches the light bulb. So the light bulb turns off. But you kept it safe. So what we do is, if that happens, we remove the old fuse, we throw it away, we plug in a new fuse, and then we flip things on again, switch things on again. How do I choose a correct rating for a fuse? You always go for like 1 to 3 amperes higher than what the device needs. So for example, if I tell you I have an air conditioner that needs 30 amperes to work, well, I had better put a what? What fuse should I use? Maybe a 32 or a 33 ampere, right? Similar to a fuse is a circuit breaker or a trip switch. This is just like the fuse. It protects the circuit if the current gets too high, if it gets too high for any reason. But it doesn't melt. This time it uses an electromagnet. We have an electromagnet over here next to what we call an iron switch, because iron is a magnetic substance. As long as the current is low, the magnet doesn't turn on because it's connected to the live wire as well. But if the current gets too high, the current goes through the magnet first. It turns on, it magnetizes, and it attracts the switch, plop, opening it. And therefore your circuit doesn't work, or your entire house doesn't turn on. It's exactly the same function as a fuse. It stops the current if it gets too high, but this time by opening what? A switch using a magnet. We always choose a rating that's 1 to 3 amperes higher than what you need, okay? And we also always connect it to the live wire. Because if you connect it to the neutral wire, this is you cutting out the current on the way out of the circuit, not on the way in. So the current's already gone in, burnt your house down, and as the current's going out, it's like, hey, you want to stop me now? Sure, go ahead. Your house is already on fire, though. Okay, that's the circuit breaker. Now, final question. What's the earth wire? The earth wire, or sometimes we call it the ground wire, is a safety feature that's not in all devices and not in all countries either. Because it's only useful if the device you're talking about has a metal case. So think of a washing machine or a computer, a PC, or a fridge, anything with metal as its outer case. The wires inside the washing machine, for example, have live and neutral connections. And if, as you connect them, one of the live wires accidentally touches the case, and you touch the case as well, the currents going to flow in not to the washing machine, but to you. So you're a nice target. And you light up. La. Now, I don't want you to light up. Okay? That's bad. So what we do is we connect a new wire to the metal case that's not part of the circuit. And we connect it to the ground or the earth. When I say ground or earth, I actually mean a big metal rod inside a building. It has to be a conductor. We just call it earthing because it's not part of the circuit. So instead of the current going through you, well, that's not a good idea. The current goes through what? The earth instead. Because which has a lower resistance? You as a human being, made of flesh and blood and bones and muscles and everything else, you've got some resistance, by the way. But the earth wire, which is made of copper often, or even aluminium, has very low resistance. The current's going to prefer that over you. Not even a current wants you. But that's good, because I don't want it either. Now, you might be thinking, but on its own, this means I'm losing electricity all the time. Well, because the earth wire has very low resistance, it causes the current to spike, increase a bit, increase a lot, which causes the fuse to trip. And phew, it's gone. So what does it do? What does an earth wire do? It protects you from getting electrically shocked if a metal case is live. Okay? If something doesn't have a metal case, you don't need a live wire. And if you have that earth wire and the fuse will blow. Okay? Let's solve the last couple of questions here. So which diagram shows a symbol for a fuse? Yay. D, obviously. And an electric kettle has a metal casing. The cable for the kettle contains a wire that is connected to the earth of the plug. Which danger does this guard against? From the cable getting too hot? No. From the casing of the kettle becoming live? Absolutely. Because if the casing is live, I get shocked. I've gotten shocked before. It's not a nice feeling at all. The casing of the kettle becoming wet? No. It's supposed to be wet. The casing of the kettle overheating? No, that's not the issue. The issue is you getting electrically shocked. So be. And you'll notice there are no more questions. This last bit, this last chapter essentially, doesn't show up a lot. It's mostly a core part of the syllabus, not an extended part. So it barely shows up. But you know what? It shows up in a multiple choice question or two, or like maybe a 1 or 2 mark question, paper 4. It could. So it's important to remember. And that, ladies and gentlemen, is unit 4, at least the first half, electricity. Next time is magnetism.